Okay, so let me show you how to get the singular value decomposition using Python. And I'm going to use a Python version that's available for everyone so that if you want to follow me, you can follow. This is called Google Colab. It's Google Colab, and you're going to see the first one. And when you click and you click New Notebook, you need a Gmail address and you have to be logged in order to use it. So click New Notebook and you're going to be getting something like this. Okay. First, we need to import some libraries because by default, Python doesn't know how to do these computations. And the library that's most popular and useful for this is NumPy. And we're going to give an alias called np. Enter. And then I'm going to also import some functions in there, which I'm going to be using frequently, which are not there. So I'm going to say from numpy.linearalgebra import eigenh. So this is for Hermitian Hermitian matrices to find the eigenvalues and the eigenvectors. Our case is real symmetric. Real symmetric are always Hermitian. Okay, so this is eigh, and then we have to normalize the vector. So I'm going to get the norm function for finding the norm of a vector. Now you type these and you have to do Shift Enter for Python to be executed. Now it's executed. And you have to do A equals to, let me use capital A. So capital A is equal to np.array. And arrays are just array of numbers, but as you can see, if you have arrays inside an array, that's like a matrix because each of these array of numbers are thought as rows of a matrix, and you put commas and then enclose them again by brackets. That gives you a two-dimensional array, which is a matrix. So we're going to define that. And I want to show you how to compute the matrix multiplication. So what you can do is A dot T, that's transpose of A, and then at symbol is matrix multiplication. So if you multiply A transpose by A, then you get this matrix, and as you can see, this is indeed symmetric, right? So these -3, -3, 2 and 2, 6 and 6, they match. So if you take the transpose of this, it's same as before, okay? Now for that, I need the eigenvalues and the eigenvectors. So what we want to do is eigh apply to A dot T at A. So because I'm using this, I'm kind of skipping the part where you find the eigenvalues, eigenvectors by hand. And I'm assuming that you know that. Okay, so let's just say that we know how to do that one. Okay, and as you can see, you get these eigenvalues. I made this matrix A so that this will in turn give me some integer eigenvalues. I thought that would be easier to handle. But the same procedure can be used for any matrix of any size. Okay, so just do this, and then you get the eigenvalues, and these arrays. This is like the matrix V, which diagonalizes A dot T multiplied by A. So that's like V, and we can assign the first one as arrays of eigenvalues, and there's a comma, and the second one is V. So the way we can assign them is say EV comma V is equal to this thing. Then if we ask what V is, now V has stored this part, okay? And what's important in this representation is that each of these columns are the eigenvectors for this one, okay? So I told you how V is constructed, right? You first find the eigenvectors, normalize them, and then put them as columns. So these columns are eigenvectors of this thing. And if you do v of 0, it gives you the very first row, which is this top row, right? If you want the first eigenvector, you need colon, comma 0, enter, and you get these values as a row vector, because in Python it's more efficient to write in row vector. So this actually gives you the row vector of the column vector, okay? It's a transpose of the first column vector. Now notice that in Python the indices start from 0. In the slides I had it starting from 1, 2, 3 all the way up till n, right? When in Python it starts from 0. So what I'm going to do now is to define the matrix U, and you do it by saying U0 is A applied to the first column vector of V, and we have to normalize this, right? So we have to divide by its size. So I'm going to take the norm of this thing. Okay, so I'm going to apply that here. And then because this is needed for U0, U1, and U2, I'm going to just copy them. Regular enter just gives you a new line. Change this to 1, 1, 1, 2, 2, 2. Shift enter. Then now I have U0, U1, and U2, and that can be used to define our matrix U, which is again np.array. It's a two-dimensional matrix, two-dimensional array, and so it's array of arrays. These are arrays, so I'm going to say U0, comma U1, comma U2, and the problem with this is, as you see, these are rows, right? So these will be the rows, and that's not what we want. And to turn these rows into columns, we should do the transpose, okay? So there you go. You do this transpose, so these will be taken as column vectors. And once we have the column vectors, great. Now we have the matrix U, and that means if we do U dot T at A, V, then we should be getting a diagonal matrix. And this is actually a diagonal matrix. This E negative 17 means it's very close to 0. It's 10 to the negative 17th power, okay? But if you don't like this, let's round it to, say, 5 decimal places. Okay, so np.round. And I need this to be rounded to decimals equals to 5. And there you have it, right? So we see that what this thing says is that A is equal to, if you multiply the U to the other side and V transpose to the other side, and then you can see that A is this, if we call that D, this is the same thing as U at D at V transpose, which is exactly is the singular value decomposition, right? So we're done, okay? Oh, I should show you what U looks like. So U looks like this. So what we just have proved is that if you have this U dotted, you do the matrix multiplication with this D and with this V, then it will be same as A. So we've succeeded in getting the singular value decomposition of A.